Hello, it's Duncan. In the last episode, we wrote 4 different versions of ParallelMap in Kotlin, using Java streams, raw threads, thread pools with futures, and coroutines. Today, we're going to pull on the thread, or maybe pick the scab, of the relative performance of the different implementations. In particular, we'll find out why the coroutines version seems to be running slower than those using native threads. And stay tuned to the end for a special bonus implementation that allows us to increase the speed of the streams version to be as fast as almost all the others. So here we are with the new IntelliJ user interface, which is prettier, I think. Okay, let's just remind ourselves how we ended up last time. We have several different versions of map. We have the Kotlin map, we have a parallel map using streams and so on. And we have this function called check and time uses our map function to take the length of 100 strings, but to simulate processing or network calls, before every one of those it sleeps for 50 milliseconds. So we expect this to take 100 times 50 milliseconds, which is 5 seconds. And when we run the Kotlin version, the one that runs in serial, it does indeed take over 5 seconds. The other versions are quicker because they're able to run these sleeps in parallel. And this function does 2 things. It tests the correctness of our algorithm by checking at least some of the output bits, and it tests how long the thing takes. We have another guide to how long things take, and that's how long the tests take to run. So you can see our Kotlin version takes 5 seconds, and our threadpool version takes 121 milliseconds, and so on. Now these timings are provided by JUnit, and they're a little bit suspect to us because they're testing the entire time it takes to run each one of those tests, not just the time it takes to call our function in here. Now we can't really affect what IntelliJ shows us here, but we could show the time it takes to run each test in the console and use that as opposed to these numbers here. So let's do that. We can say also run that. Okay, there we go. Now these numbers kind of line up with the test that we're running here. You can see 127, 123. We expect these numbers to be just a little bit less than these to account for the time it takes to be running the test around them. It's also my experience that the first test that's run seems to run slower than the others, which means I think that our coroutines version, which is consistent with being run first, is getting a bit of a bad rap. I think that what's happening is that the hotspot JIT is warming up while we run the coroutines version, and by the time we get to the others, it's running at full speed. Now, a pragmatic solution to that problem is to run the Kotlin version first. We know that's always going to be slow. We're not really comparing it to anything else. By default, JUnit runs our tests in a random order. The order is consistent for a given set of test names, but is otherwise randomized. What we can do, though, is tell it to run them in alphabetical order. We do that by going up here and saying test method order, and we can pass it method orderer method name, and that is a class for some reason. If we do that and run, then you'll see they're now in alphabetical order, but our coroutines version is still first. Now we can fix that by just giving them a numeric prefix. So if we say this is 01, this is 2, 3, 4, and 5. Now we'll run that. So now our Kotlin version comes first, and I think that's narrowed the gap between the thread pool and the coroutines version, although with one run it's hard to tell. Now each time I run this, it takes 5 seconds to run the Kotlin version, and I have to keep editing the video in order to stop wasting your time. So I think I'm going to cut this time down here to 25, and we'll just see whether that has any appreciable effect. I mean, obviously it'll make things run quicker, but does it seem to introduce any anomalies? Well, one anomaly that it has introduced is that now the Kotlin version is running too quickly. But apart from that, the timings here to be about the same, although in fact the coroutines version now seems to be looking worse. Again, though, there are random fluctuations here depending on garbage collection and a bunch of other things, so we should be careful not to draw conclusions from individual runs. Apart from that failing test, the issue here is that we were checking that it ran in over 5 seconds. Now, I don't think we're interested in the actual time it takes to run. What we're interested in is how long it takes to run compared to all the sleeping that it has to do. So previously we knew that we were sleeping for at least 5 seconds, so we expected the serial version to take at least 5 seconds. But now we've cut down the amount of time we sleep, the time it takes to run has obviously gone down as well. So I think instead of reporting the time here, we're going to report the parallelism. Let's look in check and time. If we pull out this 100 here as iterations, and this 25 here as sleep milliseconds, then we know that we're going to sleep for iterations times sleep milliseconds. So our total sleep milliseconds is iterations times sleep milliseconds. That allows us at the end to say that our parallelism is the total sleep milliseconds divided by the actual time it took. And we'll convert one of those to double to get a nice float. Now let's return that from our function, fixing the return type. And now if we go back to the places we've been asserting, then here we know the Kotlin version, the parallelism will be less than 1. It can't be greater than 1. So we say that this is parallelism, and that's going to be greater than 1. And now we're printing out, I think we could probably live without these. For the other versions, we want to change this to parallelism as well. And for all the other versions, we know that it should be greater than 1, because that's the point. And we'll judge how well they're doing by how much over 1 it actually is. But we'll get that in the printer. Completely wrong, of course, this should be that the parallelism is less than 1. Let's see whether we're right when we run the tests. Okay, good. And now you can see here that these numbers show how parallel we are being. The Kotlin version is running as if it was running on 0.8 of a processor, and this is as if it was running on 6 and 55, 37, and 19. It would be nice if we knew the name of the tests here, as opposed to having to line them up here, and we can do that with some more JUnit magic. If we ask for a parameter of test info, then JUnit will provide it to us. We can then give that to check and time, add test info to this, and use the test info in here. Well, we'll convert that to a lambda, and in here we'll say this is testinfo.playname, and then a little formatting magic of 1 decimal place format, the parallelism. We'll have to fix up our other functions. And our check and times. Something's a little bit broken, and it's because I burned the last bracket. Let's have a look. Okay, so now we had the name of the test and how parallel its particular implementation of ParallelMap is. So plain old map is not parallel at all. The parallel stream version runs 6 times faster than serial. Threads version 62 times faster, and so on. Now, what's still surprising to me about these results is the Coroutines version. If we look at our tests, both the thread pool version and the Coroutines version are running on a thread pool of 50 threads. So I'd expect them to be running at about the same sort of speed. I'm wondering therefore whether, because of running the thread pool version first, it's using up some threads that the Coroutines version isn't able to. I don't know. So remember these numbers. It's roughly twice the parallelism. And we'll just swap the order of these two round and run that. Well, that doesn't make any difference, so it's not that. We'll revert that change. And before we go on, we'll fix this spelling of parallelism before it drives us all crazy. And run again. Okay, before we go on, I'm going to eliminate a couple of things from our inquiries. They are garbage collection and shutting down the thread pool. Now, I don't actually expect that either of these is causing the thing that we're seeing here, because we have swapped the order in which the Coroutines and thread pool version run. But for completeness, we'll try and tie those down before we go on. So what I think we'll do is we'll take this thread pool out of here and here, and we'll create it as part of the fixture of the test. And we'll shut it down when the test is finished. So we'll have shutdown is threadpool.shutdown. And also once we've done that, we'll ask the system to run a garbage collection, and then finally any finalization. As far as we can make it then, that should start each test on the same sort of footing. Let's run again. And still the Coroutines version is about half the speed of the threadpool one. Now, one thing that occurs to me is that our check and time is using thread sleep, and that's not very coroutine friendly. It's realistic for us in Gilded Rose because we'll probably be blocking a thread in order to do I/O. But let's just see what the effect is of doing a delay rather than a thread sleep. So what I'm going to do is I'm going to take this one and duplicate it and make this 6 coroutines delay version. And then in here, this F that we're running is this piece of code here, this thread sleep and it length. So if we were to take that out of there and put it into here, when you can see here, IntelliJ knows that this is a blocking call, that we shouldn't really be doing it in coroutine context. But we could say delay for our 25 milliseconds. Try running that. And as you can see, that runs faster than our threadful version, which is great. And in fact, we should be able to run it without threadful at all, because now it just delays rather than blocking. Let's just check that's true. And it is. Just before we go on, I'm a bit paranoid that we might end up using different delays here and here. So what I'm going to do is I'm going to pull this out of here, make that sleep milliseconds, and just move that up to the top so it's shared by every one of our tests. Right, well, in order to allow us to investigate further the performance of this, I think what we'll do is we'll duplicate this to give us 5.5, say, and then we'll inline this ParallelMap coroutines. That inline hasn't gone all that well, but I think if we take out these, we might have something that compiles. Just run that. And somewhat surprisingly, our 5a coroutines version runs twice as fast as our 5. In fact, it runs at about the same speed as our threadful version. That's a bit weird because I wouldn't expect the cost of calling that function to be half as high as that. Let's just undo our inlining and run it again. Now that's even stranger because now we have 5 and 5a, both of which are identical code, but the second version runs twice as quickly as the first. In fact, JUnit has a way of repeating a test for us rather than us copying it and pasting it. We could say here repeated test, giving it the number of times we want to repeat, let's say 5. We could take this one away. Let's see what we get then. So you can see here we've got repetition 1, 2, 3, 4, 5. And of that test, the first one ran at half the speed of the threadful version, and the subsequent ones ran at pretty much full speed. That's really strange. It's difficult not to come to the conclusion that the coroutines is being warmed up somehow by the first run of the test, after which it runs at full speed. Now this might be something to do with hotspot, but if it is, it's hotspot optimizing the paths through the coroutines rather than the paths through the code that we're calling with the coroutines. Let's unroll this loop a bit to find out what it takes to warm up. We can make this not a repeated test, then we can take this check and time and just run it before the time that actually counts. Then you can see that the first time we print, it's running at half speed, and the second time at full speed. In fact, this time slightly faster than the threadful version. With timings, I tend to think that 10% is neither here nor there. I wouldn't draw any conclusions from two numbers that didn't differ by more than 10% without using a proper test harness like JMH. So now I'm going to inline this check and time. Now we almost certainly don't need to know about parallelism here, and we don't need our assertions either. And in here, we need to be putting the input in there. Finally, a few more little broken places. This should be just sleep milliseconds. And we don't need any of these type arguments. And get rid of the unused bits here. And I suspect we don't need to measure the time either. So we just need to run that blocking call. Okay, let's give that a go. And lo and behold, that is enough to warm up our coroutines version so that it's as fast as the threadful. Do we need to delay in order to get that speed up? Let's take this bit out and run. It seems that we don't, so at least we can warm up quickly. If we don't have the delay, then do we need the threadful? It doesn't look like we need the threadful either. How about the number of iterations? If we cut this down to just one iteration, does that warm us up? That's 32 compared to 39. That feels like it's gone down a bit. I'll run again just to check. Yes, it looks like only one iteration isn't enough to warm us up. Let's try 25. Again, maybe not enough. Back to 100. And now we see the problem of doing timings in an uncontrolled environment, because these have been consistently low. In fact, I wonder whether we really need to put our threadful back in here in order to bring them back up again. And doing that brings the coroutines version back up to the speed of the thread pool. So it looks like in order to warm up, we don't need to delay, but we do need to be using a thread pool. I wonder whether we need to be using the same thread pool. Let's inline that and run again. Well, the jury's out. That seems to be a little bit slower. Let's try again. Yes, a little bit slower, but not completely slow. So we'll return to our thread pool and let's just see how few iterations we can get away with. Can we get away with 50? Yes, it looks like we can. If we don't actually have to sleep in here, do we have to do anything at all? Can we just evaluate it? It seems that's good enough. So let's inline the whole of ParallelMap coroutines and fix up this. Check that that is still fast. Close enough. Now we appear to be doing very little. Is the coroutine scope important? Let's remove that and run. Maybe a little slower. Let's try again. It does look as if the coroutine scope helps. So we'll put that back. And now what we're doing here is we're awaiting 50 async calls. We could actually just do that with a for loop. Let's see if that has the same effect. Looks a little slower maybe. Run again. But there in fact the speed has picked up. One more time for luck. And this time the coroutines version is faster. So now we can remove this input altogether. Now at this point it does feel strange to me that we need the same thread pool here, because we're not actually doing anything that requires a thread pool. I'm going to try taking that out one more time. But no, without the thread pool it does run consistently slower. So overall it looks like 50 iterations of running some coroutines on our thread pool is enough to bring a coroutines version of our ParallelMap up to the same speed as the thread pool version. Run one more time and check. It feels to me like the coroutines version is generally lower than the thread pool version, but not by much. Maybe if we bump this back up to 100, didn't really make any difference, did it? But this time the coroutines version is faster, which suggests that 100 is about the right number. Note that our coroutines delay version down here is still roughly twice the speed of the thread pool version. I'd be interested to see what happens if we don't run the coroutine pipe clearing before it. So let's just comment this out for now and see if that affects how quickly it runs. Now, I don't know what you expected. I half expected it to be as quick as it was before, but it turns out to now be half the speed, less than that. So some of the work that we've been doing to prime the coroutine pumps with the thread pool has also helped our non-thread pool version. Revert that and run one more time. I wonder whether there's a number of iterations that will consistently make the coroutines version as fast as the thread pool version. We've been trying 100, let's try 1,000. Well, for a sample of one that made the coroutines version quicker, let's try again. This time not. And this time it's quicker. So somewhere between 100 and 1,000, it feels like we've primed the pump enough. Well, as you've been discovering if you're still watching, gauging the relative performance of pieces of code is a bit of a rat's nest. If you want to do a really good job of it, then you need a proper testing harness like JMH, which will manage garbage collection and warming up hotspot and running things in random orders. I presented a session on Kotlin performance at the first Kotlin Conf. That gave details of running a nice isolated environment on a Raspberry Pi, and also the statistical test to see whether one thing actually is faster than another. I think for today we've suffered enough, but there's just one last thing I'd like to look at, and that is a different version of the parallel stream. You can see the code for that here, and certainly on the JVM it's by far the simplest way of running map in parallel. But you see from down here that it's only running 6 things in parallel effectively. Now parallel streams are running on a ForkJoinPool, which is a specialized thread pool. And it turns out that you can in fact ask them to run on a particular ForkJoinPool. Let's write a test to do that. So I've inserted a test 3 of parallel stream ForkJoinPool version, in which case we're going to need a ForkJoinPool. And to keep things honest, we'll give that the 50 threads parallelism that we were using in other places. Now the technique here is to run the stream code on that pool. So what we're going to do is we're going to take this, and then we're going to take the pool, and we are going to submit a callable, and that callable is going to do this work. And then we need to await that. So get will return the result. Let's see how that does. And there we have it, 38.5. So we now have a ParallelMap stream that runs as quickly as the threadpool version and our warmed up coroutines version. If we inline this, and then make a method out of this, taking the ForkJoinPool, then we can take this and move it into our top level. And from the signature here, it looks as if I missed off the final get. And then this is, of course, just our ParallelMap stream. The usual breakage up here. And that should run well. So showing the natural variation, this one is now running quicker than our threadpool version. Now it turns out that this only works if our executor is a ForkJoinPool. So the type of this needs to be ForkJoinPool, not just an executor. But all these other thread pools, a ForkJoinPool would do. So in fact, over here, we can in fact use joinPool. That way it will be shut down at the end of the test, and we can remove this. And you'll see from the parallelism here that things run about as fast on the ForkJoinPool as they did on the plain old thread pool. And finally, it seems that it inadvertently moved the coroutines delay version to run before the coroutines version so that the pipeline wasn't being warmed up for it. Moving it back down to be number 7, we see the relative parallelism now in our results. Well, I think it's about as much performance work as anyone can put up with for a week, so let's finish there. Next week, we'll do what I said we'd do this week, which is look at the behavior of these different implementations when things go wrong, and use that to decide which to use for our Gilded Rose pricing service. If you'd like to see that episode, then please subscribe to the channel. If you're going to Kotlin Conf next year, which is 2023, and want to work with me in that price, then you could sign up to our TDD workshop there. And if you enjoy this, then you'll also enjoy the book that I wrote with that price called Java to Kotlin, a Refactoring Guidebook. Details of all those things, and also my talk at the first Kotlin Conf in San Francisco, are in the show notes below. Thanks for watching.